Hi, Assalamualaikum. My name is Rizal Latif. So, for the second module of Electric Electronic Laboratory, I will explain about Part A and Part B. Okay, so for Part A is about Introduction to Basic Gates and Integrated Circuit. In this experiment, you will investigate the type of logic gates contained in each IC package. Each IC has more than one logic gate of the same function. The logic gates will have at least one input and one output. So basically, in this experiment, for part A, we need to identify each IC represent of what logic gates. Okay, let me start. For the first IC package is 7402 IC, which is represent as NOR gates. So to observe the output of these gates, we need to select two digital source. Then we select this NOR gate and we connect this component with wire. Then label the wire. For the input A and the second one we label as B, and for the output we label as Y. Then we select digital simulation, click on it, change the setting to Verilog, apply it, then we simulate it, name it as NOR gate. So to get the timing diagram, select timing diagram, select this both input and the Y output, apply it. So we get the timing diagram for this NOR gate, and for the truth table of this NOR gate, we can select truth table and select the same variable. Then we're done with this truth table. You can enlarge it. That's it. This is the truth table of NOR gate, and this one is the timing diagram for this NOR gate. For the other ICs, we just need to repeat the same step again and just change the gates component. For 7400 ICs, it represents as NAND gate, and this is the result for the output for NAND gate. For 7408 IC, it represents as AND gate, and this is the result for AND gate output. For 7404 IC, it represents as inverter, and this is the inverter result output. Then for 7432 IC, it represents as OR gate, and this is the result for OR gate's output. Then you're done with the first part of this module 2. After that, as we already know the type of logic gates contained in each IC package, for the part B, we just need to build the circuit based on the diagram provided in the lab sheet. So, based on the diagram in the lab sheet, it contains 3 digital source, 1 inverter, 1 NAND gate, 1 NOR gate, 2 OR gates, and 1 AND gate. After we done connect all of these components, we just need to label the input and the output. For the first input, we label A, the second one we label as B, and the third one we label as C, and for the output we label as F. Then we select Then we select digital simulation and change the setting to Verilog, apply it, then we simulate to get the result for the output F. We save it as part B. After simulate it, we just need to select truth table to get the result for truth table. Select these three input and this one output, apply it. And for the timing diagram, we just select timing diagram, set the same variable, then we're done to get the result for this circuit. And this one for the truth table, and this one for the time diagram. After that, we try to simplify this circuit and do some calculation as I show right now on the screen. And after that, we get this type of circuit, and this is the result after we simplify the circuit just now. And we're done for the part B.
Assalamualaikum, my name is Intan Nushamin Amira binti Sharmazari, and now I will explain for part C, binary adder. Binary adder is one of the basic combinational logic circuits. The outputs of combinational logic circuit depend on the present input only. In other words, outputs of combinational logic circuit do not depend upon any previously passed input. It does not require any memory-like component, and it is one of the basic combinational logic circuits as present state of input variables. A logic circuit used for adding two 1-bit numbers or simply 2-bit is called as half-adder circuit. The circuit has two inputs and two outputs. The inputs are two 1-bit binary numbers known as oggend and addend, and the outputs are sum and carry. If you observe the sum values in the truth table, it resembles an XOR gate. Similarly, the values for carry in the table resembles an AND gate. So, to properly implement a half-adder, you need two logic gates, an XOR gate for sum output and AND gate for carry output. Half-adder is mainly used for addition of oggend and addend of first-order binary numbers. For example, 1-bit binary numbers. We cannot add binary numbers more than 1 bit as the half-adder cannot include the carry information from the previous sum. Due to this limitation, half-adder is practically not used in many applications, especially in multi-digit addition. In such application, carry of the previous digit addition must be added along with 2 bits. Hence, it is a 3-bit addition. So the next one is the full adder circuit. A full adder is a combinational logic circuit which performs addition on 3 bits and produces 2 outputs, a sum and a carry. As we have seen that the half adder cannot respond to 3 inputs, and hence the full adder is used to add 3 digits at a time. It consists of 3 inputs, of which 2 are input variables representing the 2 significant bits to be added, whereas the third input terminal is the carry from the previous addition. The 2 outputs are a sum and carry outputs. From the truth table, we can obtain the Boolean expression for both the sum and carry outputs. Using those expressions, we can build the logic circuits for full adder, but by simplifying the equations further, we can derive at a point that a full adder can be easily implemented using 2 half adders and an OR gate. Addition and subtraction are 2 basic arithmetic operations that must be performed by any digital computer. If both these operations can be properly implemented, then multiplication and division tasks become easy. Okay, now let's look at the experiment that has been done and look at the result. Each binary addition gives sum as 1 bit, either 0 or 1. For single bit addition, there may not be an issue. The problem may arise when we try to add binary numbers with more than 1 bit. The next one is subtraction. Subtraction is a mathematical operation in which one integer number is deducted from another to obtain the equivalent quantity. The number from which other number is to be called deducted is called a minuend, and the number subtracted from the minuend is called subtrahend. These are the experiments that has been done and also the result. So we can conclude the experiment for part C binary adder were presented by building a testing, half adder circuit and full adder circuit. The result recorded is expected and the objectives are achieved. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shamila binti Zainab, and I'm going to explain about the flip-flop, and then we will go next to the experiment of the flip-flop, which is SR flip-flop, D flip-flop, and ZK flip-flop. But before we go further to the experiment, I'm going to explain about the basic of the flip-flop. So what is flip-flop? Flip-flop is one of the standard bistable circuit which is needed to construct a simple sequential logic circuit, which is SLC. SLC has a memory built in the circuit, and it is dependent on the present input and the past output, which what we call a memory. So SLC is not like combinational logic circuit. Have you ever heard of it? I'm sure you have, because it is a basic circuit before we learn about the flip-flop. So combinational logic circuit is a circuit that changes state depending upon the signal that is applied on the input at that time. So the diagram is like this one. So as you can see at the diagram, A, B, and C is the input, and then it will produce next straight to the output. But it is different for SLC, because in SLC it's like having a feedback before the output, and then that what we call a memory that is latching the circuit. And SLC have three states, which is present input, present past input, and past output. So it will remember these three conditions and stay fixed to its current state until the clock signal change one of these states. So the word sequential means that one thing will happen in sequence, one after another, and actual clock will determine when things will happen next. So as you can see, diagram like this. So it is the same like combinational logic circuit, but before the output it will have the memories that goes to the that will latch on the input, latch back on the input. But as you can see there, it has a clock signal that interrupt the feedback. So next we will go straight to the experiment. So now I will continue to demonstrate the simulation of the flip-flop in Proteus. I will not be using QUCS. For now I will be using Proteus. So first of all, let's click on the component mode, and you can find the component that you want here on the keywords toggle, and then after that you just click on the component that you want. Okay, so now I click on the NOR gate and put on this here, 1 and then 2. Okay, after that I will be using a logic toggle. As an input, and then the logic toggle here, and I will be using logic probe. Here and here. So after I've collected all of the component, I will connect it with wire. Just connect it together. And after you connect all of the wire, you can rename the component as you see fit. In this sidebar here, you can find it here, A. Just click this one, and then you can set what name do you want to put in. After you have renamed all of the components, so we are ready to simulate the circuit. Okay, first of all, let's try to simulate 0 and 0. First of all, let's put the input for reset and set 0. Let's see what happened, okay? So now we simulate by clicking this one, and then we can see the error warning. So you can, in SR circuit, you can put the input 0 and 0. So now let's change it. Let's apply a pulse on reset. And then let's simulate it again. So now we've got A at 0 and the output here. Okay. We can compare, because we use the NOR gate to make an SR circuit, we can compare the NOR gate truth table to get the output out of SR flip-flop. So first of all, 1 and 0, we can get 0 output here based on the NOR truth table. 1 and 0, we can get 0 here. And then this 0 will go down to the lower part of the NOR gate. And then this one will become 0 and 0. So at lower part of the NOR gate, which I will call it as NOR gate B, has 0 and 0 input. So based on the truth table, 0 and 0 input of NOR gate will get 1. So here it will get 1. So 1 will go to the NOR gate A, and this one will become 1. So now the latch is storing 0 as its memory. So after it's storing 0, we have to reset it again by remove the reset here and apply a pulse at set. Then this will change. Just now the latch contained 0, now it contains 1. So 0 and 1 will get an output of 1. And then 1 will go to the NOR gate B. Then based on the truth table of NOR gate, when one input meet another one input, it will produce 0 input. So now 0 will go up here to the NOR gate A. So what is the latch, the memory that is latch 8 input here, which is 1. The latch is store 1 now. After that, we can remove both of these apply pulse to 0. Now let's stop the simulation. So after we remove the set to 0, it will become low. And then now we realize that the previous latch memories is still there, even though we have changed the state to 0 and 0 to the low state. Okay, the previous memories in the latch is still there, which is, you can see that what is produced at the truth table here, 0 is 0, no change, because the memory is still there. Now let's see to the what happened when we set and reset to the height pulse, which is 1. Put it here 1. Let's see what happened here. Just focus on A and B here. 1 and 1. Okay, so now it becomes 0. So let's see what really happened in this circuit. Okay, we know that the output will become 0 and 0, but let's manually deduce this circuit. So first of all, 1 and 1. For the NOT gate, it will become 1 and 1, it will become 0. Then 0 will be here, and then it will go down to the NOT gate B. And then let's see, input 1 and 0. For input 1 and 0, the input will also get 0. So 0 will go up here to here, and NOT gate E. And then again, 1 and 0 will become 0 again. It will be an endless cycle. So it is impossible, it is invalid to have set and reset as 1. The input is 1. So this part here is invalid because it will be an endless cycle. So it is really race against time for these two input to see, to race and see if you want to produce new input. So now it is endless because it always produces 0. So if you want to produce 1, it will be race against times, because let's see here, if 1 and 1, it will race, the input will race with each other to see who will get a new input first. So it is impossible to read the value like that, and it is impossible to determine which one will get the new output first. So for the set and reset with input 1, it is invalid.